Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Today, we are taking a massive leap. We're moving beyond the simple push and pull forces we all know.
Our mission today is a real deep dive into analysis. We want to understand how engineers break down scenarios where forces just collide. You've got bending, twisting, and pulling all at once.
All happening in the same place.
We'll look at how they calculate things like stiffness and deflection, and maybe most importantly, how those elegant classical theories laid the groundwork for the powerful computer tools we have today.
That's the key connection, isn't it? The bridge from calculus to computer science. I mean, you think about an aircraft wing or an offshore rig. The stresses inside are just not simple and uniform.
Not at all.
You're dealing with these incredibly complex, non-uniform stress states. So you need pretty advanced techniques to figure out, both the structure's ultimate strength and its day-to-day stiffness.
Okay, so let's start where that complexity really begins, with combined loading. We know about direct axial stress, but what happens when we take a column, say, and the load isn't perfectly centered?
That's where it gets interesting, because what engineers do is they simplify it. An eccentric load P, that's a load that's just a little off-center, is statically equivalent to two separate effects.
Two things at once.
Yep. It's like having a pure axial thrust, P, right at the center, plus a bending moment, M. And that moment is just the load P times its distance from the center, E.
P times E. So you're not just compressing the column, you're actually bending it at the exact same time. You have two different stress profiles just layered on top of each other.
Precisely. You have the uniform compressive stress across the whole section from the thrust, and then you have the bending stress compressive on one side, tensile on the other.
And the final stress is just the sum of the two.
You just add them up. Algebraically, it's that simple.
That has, huge implications, especially for construction, right? I'm thinking of materials like stone or masonry, things that are just awful in tension.
Absolutely. Think about an old stone arch bridge. You have to guarantee that under normal loads, you never generate any tensile stresses.
Because it'll just crack.
Instantly. And this is where that famous rule of thumb comes from. For a solid rectangular section, to keep all the stress compressive, the load has to fall within the middle third of the section.
The middle third rule.
Right. If that eccentricity is greater than 1/6 of the depth, you start pulling the other side into tension, and that's where you get failures.
So a simple design rule born from just summing two stresses. Okay, let's shift gears. If direct stress is the push and pull, what about the slip and slide? Let's talk about shear.
A completely different animal. Shear acts tangentially to a surface.
And the key concept here is something called complementary shearing stress. Right.
It's essential. You just can't have shear stress on one plane by itself. It's physically impossible. If you imagine a tiny little cube inside the material, if there's a shear stress pushing the top face to the right,
then the whole cube would just start spinning, wouldn't it?
it would start spinning. So to stay in rotational equilibrium, the material has to generate an equal balancing shear stress on the perpendicular planes.
So a shear down one face means there has to be a shear sideways on another.
Exactly. Tau SI must always equal tau IX. It's a fundamental truth that underpins everything from torsion in shafts to, complex beam loading.
Which brings us to the really complex stuff. What if you have a general two-dimensional stress system? You've got direct stresses in the x and y directions, plus that shear stress, tau I. The material's being pulled, squashed, and twisted.
All at once.
How do engineers even begin to find the maximum stress in that mess? The math seems like it would be a nightmare.
Oh, it is. And that's why the idea of stress transformation is so powerful. We know that if we could just rotate our little elemental cube inside the material, there must be two specific planes, exactly 90 degrees apart, where the shearing stress is 0.
The shearing stress just vanishes completely.
It vanishes. It's the cleanest way to look at the forces. We call those the principal planes.
And the stresses on them are the principal stresses.
That's right. Sigma 1, the maximum direct stress, and sigma 2, the minimum. When you're analyzing for failure, these are usually the first numbers you look for. They tell you the absolute peak direct stress that the material is feeling anywhere.
But like I said, calculating them with trigonometry, all the sines and cosines, sounds awful, which is where a famous graphical shortcut comes in.
And thank goodness for it. This brings us to one of the most, elegant tools in all of engineering, Mohr's circle of stress.
So instead of pages of equations,
You just plot 2 points. You take your known stress states, your sigma x with tau psi, and your sigma y with negative tau psi, plot them, and then you just draw a circle that connects them.
and suddenly every possible stress state on any plane is right there on that circle.
It's an incredible visualization tool. The coordinates of any point on that circle tell you the direct and shear stress on any inclined plane you want.
And the radius of the circle is?
The radius is your maximum shearing stress, tau max. It's that simple.
So you can instantly find the maximum shear. And you know what happens on planes that are 45 degrees away from those principal planes.
Yeah.
It's an immediate check for shear failure.
Exactly. Now, here's a critical little detail, a caveat that really separates a good analysis from a safe one.
Yep.
We always simplify things to 2D, but we live in a 3D world. Even if we have our circle and we find our tau max, we have to remember the third principal stress, sigma 3, which might be 0.
And why can't we just ignore that?
Because failure by shear depends on the largest difference between any two principal stresses. The true maximum shear might actually be between sigma 1 and that 0 stress from the third dimension. That 3D reality can be what actually causes the material to yield.
That's a huge insight. Even in a 2D problem, you have to think in 3D for safety. Okay, we've been focused on internal forces. Let's pivot to the structural response itself. Let's talk stiffness and deflection. Why is calculating how much a beam bends just as important as making sure it doesn't break?
It really boils down to serviceability and stability, too. I mean, you can design a floor beam that's strong enough, but if it sags too much, the ceiling plaster underneath cracks, the floor feels bouncy.
It fails its function, even if it hasn't broken.
Precisely. And beyond that, you actually can't solve statically indeterminate problems without considering deflection.
Right, those are the ones where you have too many supports, too many unknown forces for basic equilibrium equations to handle.
Exactly. A beam on 3 supports is a classic example. You can't solve it with forces alone. You have to use the fact that you know the beam's deflection at those supports. You bring in deformation analysis.
So we need a way to calculate the exact deflected shape. Where does that begin?
It starts with the fundamental equation of elastic bending. The core relationship is that the bending moment, m, at any point along a beam, is proportional to the curvature of the beam at that same point.
And the constant of proportionality is that key property. The flexural stiffness, E times I.
That's the one. E is Young's modulus. That's the material property.
And I is the moment of inertia, which is all about the cross-section's shape.
You got it. And that gives us the famous differential equation. EI times the second derivative of the deflection equals the moment m. You integrate it once to get the slope, integrate it again to get the actual deflection.
We see those nice, clean formulas in textbooks for simple cases. But I imagine when the loading gets messy or the geometry is complex, integrating those equations over and over is...
It becomes a huge chore.
Girl.
Or even impossible. And that brings us to one of the most powerful, most elegant tools in all of classical mechanics. It's the real bridge to modern methods, energy methods.
Specifically, the principle of virtual work. Now that sounds almost philosophical. What is virtual work?
It is a bit of a mind bender, but it's a genius concept. Imagine a structure is in perfect equilibrium under its real loads. The principle says that if you then apply a tiny imaginary virtual displacement to it, the total work done by all the forces, internal and external, has to be 0.
Okay, so how does that help us find a real deflection?
We use it like a trick. Let's say you want to find the deflection, delta, at one specific spot on a complicated frame. You apply a unit virtual load, a pretend force of 1, at that exact spot in the direction you care about.
A fake force.
A fake force. Then you say the external work done by this fake force, which is just 1 times the unknown deflection delta, must be equal to the internal work done by all the real bending moments inside the structure.
So instead of solving a massive equation for the whole beam shape, you use an energy balance that's focused only on the one point you care about.
Exactly. It turns these impossible calculus problems into integrals you can actually solve. It's an indispensable tool for complex frames, trusses, curved beams, things you couldn't solve otherwise.
And what about complementary energy? Is that a similar idea?
A very close relative. It's another powerful shortcut. Complementary energy lets you find the deflection by just taking the partial derivative of the structure's energy with respect to the load causing the deflection. It's just another brilliant way to get to the answer.
It's amazing that these tools could handle such complex frames, but even they have limits when you get to, say, a modern skyscraper. This feels like the point where we need the digital leap.
That's exactly right. When you have thousands of elements, thousands of degrees of freedom, you can't do it by hand. You're solving thousands of simultaneous equations, and for that, you need the language of computers. Matrix algebra.
How did matrices become the language of structural analysis?
Well, a matrix is just a really organized array of numbers, and the operations you can do with them, like multiplication, let computers process huge amounts of data incredibly efficiently. This was the backbone for the matrix displacement method, which really changed everything back in the
And
1940s.
it started in the aircraft industry, right?
Yeah.
Why there specifically?
Speed and weight. Aircraft have to be strong, but they have to be ridiculously light. They needed a fast, reliable way to analyze these really complex, highly indeterminate structures where every single ounce matters.
And the core idea is to break the whole structure down into simpler pieces.
Exactly. You treat the whole thing as a complex spring system, and then you subdivide it into simple elements, like individual rods in a truss. The analysis then just focuses on the connection points, the nodes.
And you build a massive system of equations based on how those nodes connect.
Correct. You establish the force displacement relationships at every single node, and you assemble it all into one giant master equation. That's defined by the system stiffness matrix, which we just call K. The computer solves that one huge equation, and poof, you get all your displacements and stresses.
And that matrix displacement method is the direct ancestor of the tool that every engineer uses today, the finite element method, or FEM.
FEM is just the modern commercial application of that method. It's the most powerful tool we have. It can analyze anything from the tiny legs on a circuit board to the huge drilling rigs out in the ocean. And it shows that whether you're using a pencil in virtual work or a supercomputer, the underlying physics of equilibrium and compatibility are exactly the same.
So we started with a simple bend in a column, visualized the stress with a circle, calculated the sag with an energy trick, and we've landed at the foundation of all modern computer-aided engineering. What a journey.
It is, and it brings us all the way back to the material itself. I mean, this whole discussion has been about elastic analysis, where stress is proportional to strain. But you have to remember how ductile materials like steel actually behave.
Right, they don't just snap at the yield point.
Not at all. They absorb a tremendous amount of work through plastic deformation before they actually break. That ability to absorb energy is a critical reserve of strength.
Which raises the final thought.
Yep.
We've been focused on keeping structures within their safe, elastic limits.
We have. But here's the thing. Those same principles of virtual work that we used for elastic deflection, they can also be used to predict the plastic collapse of a structure. So here's the question. Why is knowing that collapse load often a more realistic and maybe even a more reliable estimate of a structure's true safety than just checking its working stress limits?
Because even if one part of the structure starts to yield, the overall collapse load tells you how much reserve strength the entire system has before a catastrophic failure mechanism actually forms. It's a clearer picture of real-world safety than just looking at the first point of yielding.
Exactly. That structural reserve strength is what holds the built world together. Something to think about as you walk through a world built on stress, strain, and some truly beautiful mathematics.